I'm very happy to introduce Professor Mark Fox to give our seminar today. So Mark is a professor of industrial engineering, as well as distinguished professor of urban systems engineering, and the associate director of research at the School of Cities. And in fact, this whole seminar series was originally his idea, to try to get a bunch of different people from across various disciplines talking about supply chain issues. And so the fact that we're here is due to him to a large extent. Mark has an extensive experience both in academia and in industry, having founded 2 startups, as well as publishing over 200 papers. And he's a fellow of the American Association for Artificial Intelligence and the Engineering Institute of Canada. So he comes with us with a lot of experience. His most recent research has looked at artificial intelligence as it is applied to smart cities, where he's developed ontologies for the representation of city information and knowledge, which are being adopted by cities around the world. And so today he's going to talk to us about ontologies, and in particular how ontologies are related to supply chain performance. So over to you, Mark.
Thank you very much, Chris. I presume you can see what's on the screen now?
Yes.
Okay, great. Let me see if I can remove that. You're watching the screen.
No, we're not seeing that, so.
Oh, you're not seeing it? Okay, good. Okay, so my original title was The Role of Ontologies in Modeling and Measuring Supply Chain Performance. And then I saw Chris's talk yesterday, or last week. I decided to change it to The Role of Ontologies in Modeling Supply Chains. Okay, so this is going to be a more basic talk on ontologies than I was originally planning, in that we'll address a number of questions, such as what is a knowledge representation, for those of you who are unfamiliar with that. And then what is an ontology? And then we'll talk a little bit about the semantic web, and then I'll give an example of its application within the supply chain, and in particular, traceability within the supply chain. And then I'll end off with a message from our sponsor talking about city data ontology standards on one slide or so. So why don't I just dive right in? So I want to talk about ontologies, and I want to talk about the supply chain. I do have a bit of a history in supply chain research back when I was doing scheduling work along with Chris. And before that, in the 80s and 90s and the first decade of the 21st century, I no longer do scheduling related research. And focus more and almost in my entirety on knowledge representation, in particular the design of ontologies for cities. Now, the whole world of ontology grew out of what was called knowledge representation, still is knowledge representation and reasoning within the field of artificial intelligence. And so what I first want to do is talk a little bit about what is a knowledge representation, so that we're all on equal footing in this area. And this is based upon a paper written almost 30 years ago by Davis, Schroep, and Solovitz, sorry. And it's actually a very nicely written paper that you could go back to. Anyway, so why do we care about representing knowledge? And I think Davenport and Prusak said it best, again, going back 25 years or so, that the only sustainable advantage a firm has comes from what it collectively knows, how it efficiently uses what it knows, and how it readily acquires and uses new knowledge. Now, this was written at a time when knowledge management systems were in vogue, and major companies were building systems to acquire, represent, store, and make available different types of knowledge within their organization. And even though that goes back to the knowledge management days, it is as true today as it was back then, in particular where computers play an increasing role in day-to-day decision-making. We have to answer the question, what is knowledge and how is it represented in a computer? So that's sort of the motivation, is that everything we do today, especially computer-based, is based upon some representation of knowledge. And so we need to step back and ask ourselves a basic question: what do we mean when we talk about representing knowledge? So from the knowledge representation perspective, a knowledge representation is a surrogate, a substitute for the thing itself. And so in this picture, what we see here is a distinction between the actual chair that physically exists in the world and the chair that exists in our mind. And the reason why we refer to knowledge representation as a surrogate is that when we reason about the chair, we're not actually reasoning about the actual physical chair. What we're reasoning about is a representation of that chair. And by definition, since what I have in my mind is not the actual chair, it is not a precise representation of that chair, it is a surrogate for that. And what I represent about that chair will be different than what is actually the chair represents. And so what can we create surrogates for, and why is being a surrogate important to understand? Well, we have surrogates for two types of entities. One is tangible entities, things that exist physically in the world, such as buildings, cars, roads, etc. These are referred to as natural objects. And there are intangible entities that do not exist in the world, such as categories, beliefs, processes, causality, mathematics. And so we do have representations for things like E equals MC squared in our brain. And if you ask the question about these surrogates that we have in our brain, and more importantly, these surrogates that we have in our computers, the question becomes, how close is a surrogate to the real thing? That is, what attributes of the original does it capture and make explicit, and what attributes does it omit? And we refer to perfect fidelity as being, is in general being impossible. Because perfect fidelity means our representation in our mind or in our computer is exactly everything that is embodied in the thing that we're representing. So exactly everything about a chair, every molecule, every atom, etc., that one can associate with that chair is absolutely impossible for us to represent. It's impossible for us to know. And so it's impossible in principle. And therefore our surrogate, our representation in a computer or in our brain, is different from the thing itself. Oops. Let me get that back. So the level of fidelity of the representation is really what we're interested in. What level of fidelity do we need? That is, how perfect a surrogate do we need in our representation? And that is determined by whether that level of fidelity that we have is fit for purpose. And so what do I mean by fit for purpose? Let's consider the following example. So consider the problem of creating a program that will recommend the type of wax to put on snow skis. What information and knowledge would you need to represent? Okay, well, think about it. If I was born and raised, grew up in Florida, my representation of snow would be rather limited, okay? I'd be limited to being this white stuff that's cold, okay? And that's about it. And why? Because I don't experience snow that often, and the only thing I need to know is I better put something on warm because it's snowing outside, as opposed to running out and jumping around saying, hey, this is snow. So the representation that is fit for purpose is rather limited in terms of what we represent, temperature, color, maybe that's about it. So that representation is fit for purpose. On the other hand, if I'm a skier, I actually have a richer representation. I have a high fidelity representation where I represent things such as powder, crud, corn, grapple, crust, dust on crust, mashed potatoes, Sierra cement, for those of you who do skiing for real. This is all important because it will change the way you ski. It will change the way you prepare your skis in terms of wax and other things in order to maximize your skiing ability. And so again, the issue here is dependent upon what I'm going to use my representation, my knowledge representation for, I'm going to have a differential level of precision in the representation. And the consequence of that is that imperfect surrogates, imperfect fidelity, is that any reasoning done with the representation will eventually lead to incorrect conclusions, independent of the soundness of the reasoning process. So the question we face is, again, this issue of fit for purpose. What is the appropriate representation? How high fidelity should I have? And that is ultimately driven by what the application is, what the nature of the reasoning is that I want to perform. And so that again raises this issue of what should I represent? How should I represent? So that leads me now to the next stage, next step in my presentation, which is what is an ontology? Because the answer to the question of not what should I represent, but how I should represent it is addressed within the world of ontologies, or what I'll often refer to as an applied ontology, because we often, people who are not familiar with the computer science side of ontologies will mistake ontology for the interpretation of the word ontology for what exists within the domain of philosophy. And we're not talking about the philosophical interpretation of ontology. We're talking about a very pragmatic interpretation of ontology, which is focused on how do we represent knowledge that we can then use in a reasoning system. So an ontology is actually more than just a reference model or vocabulary of terms. An ontology, and this is the answer to the question, is a precise, formal, using a logical language, representation of the meaning of the concepts and properties within the domain of interest that you have. And what makes an ontology interesting is that it answers the questions: what are the core concepts and properties that span the domain's data? That is, what are the core concepts I need to be able to represent within the domain of application? And to what extent can we generalize them in a useful way? So what distinguishes this from somebody just building a data model, an ad hoc data model, is the extent that we can generalize the underlying core concepts and properties so that they can be applied across multiple applications. So we're looking for a very general set of core concepts and properties that span the many applications that we may be facing. And the second question that an ontology answers is, what are the key distinctions? Can we formally define the necessary and sufficient conditions using properties for something to be an example of a concept? And this comes into play in our example of snow. The question then becomes, if we're going to represent snow for a skier to use, what are the key distinctions sorry, I'm looking one slide ahead, and I didn't know I was one slide behind on the screen. So the question becomes, what are the necessary and sufficient conditions to distinguish one concept from another, to distinguish crud from popcorn, snow, et cetera, et cetera. So hopefully I'm motivating you a tiny bit as to what an ontology is and what are the core ideas that differentiate it. Now what I'm going to do is I'm going to take you into actually what an ontology is composed of. And an ontology, from my perspective, is composed of 3 levels. The lowest level of the ontology is what I refer to, or is what is referred to as a knowledge graph. The graph is composed of nodes and links. The nodes can be classes or concepts, that is, general concepts that exist within your domain. The arcs can represent properties, or links represent properties. The nodes can also represent instances. So you can imagine a class that represents the general class of chair, and an instance being a particular chair that exists within the physical world. And so each would be nodes, and they would be linked together. In addition to that, a knowledge graph is often boosted with the ability to represent taxonomies, classes and subclasses. So there are links in or arcs in this knowledge graph that represent that one node is a subclass of another. And the fact that one node is a subclass of another, such as you have a chair as a class, and then you maybe have an office chair as a subclass of chair, that an office chair can inherit properties of the chair class through the taxonomic relations subclass of. Let's look at a bit more real example. taken from the area of transportation planning, which is relevant to the whole supply chain. Transportation planning in this case predicts transportation demand over a multi-decade horizon. And in order to predict demand, we have to simulate how a city or a supply chain will change over the time period of interest. Often in transportation planning, it's decades. For example, how households and their members will change over time, and their changing requirements as the people, the members of the household, grow older. We're taking this out of the work that we have been doing with the Transportation Research Institute at the University of Toronto. And I believe Megan Katsumi is speaking next week, and she'll give everybody a deeper insight into what the ontology that was developed within the Transportation Research Institute. But this is where this example is being drawn from. So if I'm going back to that level of knowledge graph, the types of nodes, that is classes or concepts that exist within the knowledge graph, include things like residents, households, links such as one person being a member of a household. We have classes that deal with transportation networks, that deal with the types of transportation vehicles that exist out there. Those are all nodes and links that exist within the knowledge graph level. Now, the next level is where we have definitions and constraints, and this is where the use of logic comes into play. The definitions constraints within an applied ontology allows us to define the classes in terms of their properties. And through the use of these definitions, we can do a number of things. We can do automated classification. That is, we can recognize whether some instance is a member of a class due to the definition of the class. We can do verification of data, that whatever data that you're receiving through the supply chain conforms to the definitions of the classes that it's supposed to be an instance of or a member of. We can do deduction. We can infer new things about these things that exist within the supply chain based upon it being an instance of a class. There's a variety of things that we can do if we have definitions and constraints on these classes. So this is an example of a definition. A Toronto resident resides in, owns property, or owns or operates a business in Toronto. That's a definition of a Toronto resident. Another definition is a household is composed of at least one person who resides at the same address. These are all examples of definitions that one would then capture in the form of a logic and be able to represent directly in our ontology. The third level is our microtheory, and this is where we have axioms or rules defined, and we can perform deduction using these definition constraints and these rules. An example is of a rule is for each year above the age of 14, a member of a household will leave that household with some probability p age, which I haven't defined here, but it's some probability distribution based upon age. So those are the three levels of an ontology. The knowledge graph, which is a graph structure where the nodes and arcs are labeled as classes or instances and properties that link the different nodes amongst them. Definitions and constraints that are used to define the classes and properties at the knowledge graph level in terms of a logical language, and the microtheory level where we can define rules and also use the class definitions, etc., for performing deduction, in addition to using the rules to perform deduction. Now, is this notion of an ontology just some abstract thing that us AI people have created and sits within the realm of just AI people, or is it something that is actually finding its way into use within the broader world? I'm going to answer that question quickly with some examples of knowledge graphs. Some of you may use Google, or I should put it another way, everybody uses Google. When you go to a Google site, when you go to Google and you type in Justin Trudeau, you get a page that looks like this. And in addition to that, you get this box on the side. It tells you, gives you a description of Justin, when he's born, where he's born, height, spouse, party, education, children. Okay. Now, the question is, how does Google do this? How does it generate that page of information? Do they have a bunch of people who are sitting there filling in templates for these sidebars for everybody of interest out there, and then they just display that? Are they dynamically reading all the pages that exist across the internet and somehow using natural language processing generating all this information? Or is there some other method? And the answer is there is some other method. Google maintains a knowledge graph that contains over 70 billion triples. That is, a triple is one node with an arc leading it to another node in a knowledge graph. So basically 70 billion arcs with a node at each end, running over thousands of servers, which is then used to represent knowledge about millions, if not billions, of entities that are out there, such as politicians like Justin Trudeau. And it queries the knowledge graph to pull in the information that's put in that sidebar. That knowledge graph is built by going through web pages all around the world and extracting bits of information and putting it into the knowledge graph. Apple Siri has a knowledge graph sitting on your phone, so that when you're talking to Siri, it uses knowledge graph to bridge between the speech processing, that is the sound to text, and the answering the question. LinkedIn has a knowledge graph. It's called their economic graph, and since their acquisition by Microsoft has their knowledge graph, which is integrated with LinkedIn's knowledge graph. And Airbnb has their own knowledge graph, which provides a systematic approach to storing and serving high quality information about entities, relationships, cities, landmarks, events, et cetera, et cetera. So this knowledge graph technology, as you can see, has found its way into use around the world on major platforms around the world as we speak. So let's get to the next level. The ontology example, where we're looking at the definition of classes and properties using logic. What I'm going to do is address the problem of determining city residency, because I focus a lot on cities now. One issue that arises is determining whether a particular individual who is in a city is eligible for particular services of the city. And so what you want to do is somehow figure out, based upon the information about the individual, whether they satisfy the city's definition of being a city resident. Now, this isn't some learning algorithm that you're using, because there's an explicit definition of who is a resident of the city of Toronto, just as there is for Beijing, as there is for a German city, et cetera, et cetera. These are not something you learn. This is something that's explicitly stated in the laws of that municipality or that country, et cetera. And there's a lot of knowledge out there that is explicitly defined and are not something that is just learned over time. And so if we had an ontology, and in that ontology, a city ontology, and in that ontology we represent the definition of a city resident, we could use that to verify that a person who requests service is a resident, or given a database of people who live in the city, we can determine who are residents of the city, or if we have to validate manually whether somebody is a resident of the city, we can use that, or we can infer characteristics. We can infer characteristics of the residents. So the previous bullet is validating manually provided classifications of residents. So how would an ontology help in this situation? Well, let's first take a look at some of the definitions of city residents around the world. Toronto, you are identified as a resident if you reside in, own property, or own or operate a business in Toronto. Beijing, all individuals holding nationality of People's Republic of China who have a domicile in Beijing and nowhere else. If the individual maintains a regular dwelling somewhere else, the more regular dwelling is considered their place of residence. And then New York has theirs. Germany has a resident of Germany generally refers to an individual as a domicile in Germany or spends more than 6 consecutive months in Germany. Anyway, variety of definitions out there, rather interesting. Let's see how an ontology represents that definition so it can be applied for validating somebody's residency. Here is the knowledge graph that we would represent. Now, note, we capture the main concepts in here: Toronto resident, subclass of a resident, owns property in Toronto, resides in Toronto, operates a business that has an address, and that address has a property called InCity Toronto. So most of the stuff here, most of the ideas, the properties, and the concepts that exist in this definition, you can find in this knowledge graph. But nowhere in this knowledge graph is there an actual statement that the following defines whether somebody is or is not a resident. To do that, we have to then introduce our logical language. So in this case, and this is a simplified specification of logic, Toronto residence is a subclass of resident and resides in Toronto or owns property in Toronto or operates a business, and that business has an address, and that address is in the city of Toronto. So this brings us pretty much to the point of being able to represent this sentence explicitly and being able to apply it explicitly to verify that somebody is actually a resident of Toronto. Or if I were to say, Chris is a resident of Toronto, I know that he either resides in Toronto, owns property in Toronto, operates a business with an address in Toronto. I can infer that from the assertion that Chris is a resident of Toronto. Now, the actual representation of that logical statement is a little more complicated when you look at it. That's why I don't like to show this version. But it basically captures, it provides the explicit representation of this, where Toronto residence is equivalent to resident. This is our conjunctive operator, and has a resident that's a property, which is a residence, which is a concept, and there exists an address such that the city of that address is GN 6167865. This is a unique identifier on the internet that uniquely identifies the city of Toronto. Actually, I'm not going to get into these, what are referred to as geonames, unique identifiers for places. But if you step through all of this, which we are not, you'll find that this is an explicit representation of the definition that we saw before. So what's the bottom line on this? I showed you how to represent a Toronto resident. But the key takeaway here, and it gets back to what I said earlier, the purpose of the ontology is to identify the core concepts and properties that allow us to represent these definitions and allow us to represent what distinguishes one definition from another. And that means that we're not creating our ontology is not uniquely defining Toronto resident, nor Beijing resident, nor Mumbai resident. Our ontology is providing us with the core set of concepts and properties with which we can construct these definitions. So this is really where the ontology is. We use this we apply this ontology to the representation of these definitions. And so that's really where our focus is. What are these core concepts and properties that we can construct these definitions with? Now let's just go to our third level of an ontology, the microtheory example. This is for each year above the age of 14, a member of a household will leave with a probability of P age. This is within the ontology a representation of that axiom or rule, which basically says the same thing, and I'm not going to take the time to go through it at this particular moment. Basically says what we say over here. But you can now use that rule to infer when it is an individual will leave a household. Now, I've talked about ontologies, I talked about fidelity, I talked about core set of concepts and properties, etc. I've talked a little bit about how you could use this in the application of residency to individuals in a city. Basically, the major impact that ontologies are having today is on addressing the semantic interoperability problem. And semantic interoperability is the ability of computer systems to exchange data with unambiguous and shared meaning. You could imagine within a city, you could have people in the water and sanitation department that when you use the word plant, the term plant, they think of a sanitation plant. When you talk to somebody out of Parks and Recreation, and you use the word plant, this is what they think of. So even simple things like this are problems within a city because all the different departments in a city evolve separate from each other in silos. They are legacy departments. They develop their own terminology, their own interpretation of the terminology, etc. And the challenge that we have within cities and across the supply chain is the integration of data from across multiple sources, multiple departments, both within cities and across the world, because there are different interpretations of the terminology. And solving the semantic interoperability problem is a requirement, and if we're going to achieve supply chains that are well managed. So what are the sources of the meaning of the data? How can we achieve semantic interoperability? Well, we create these ontologies. That's what it's all about. But the problem of getting there is a real challenge. You just can't take data and say, look at the data, and you can figure out what the ontology should be, because the actual interpretation of any data that exists is in the brain of the software developer. And so reaching out to that software developer to try and understand what the semantics are, the meaning are of the data that a particular application program is producing, of a particular data set is a major challenge. And part of the challenge is, we don't have access to the developer, so we have access to documentation. But the problem is documentation is either sparse or non-existent or generations behind. It's never maintained at the level that needs to be, and it may be poorly written also. So your alternatives to look at source code, if you can understand it, but the source code is never available to you. And so the basic problem is that the semantics, the meaning of the data that you're looking at that's coming from various departments within a city or across various organizations and countries, et cetera, across the supply chain, is that the meaning of the data is not separated from the code that generated. That is, in order to understand the meaning of the data, the semantics of data, you need to look at the code, and that's impossible. So the whole point of achieving semantic interoperability is to have the semantics associated directly with the data, and the way we do that is with ontologies. Using ontologies, we can define the meaning of the data separate from the code that generated, separate from the mind of the person that generated. It generates separate from the documentation that is there. And so with these ontologies, we can achieve semantic integration, data integration. The ontology can serve as an interlingua. Data from multiple systems can be mapped into it, allowing for consistent interpretation. We use it for model checking, as I talked about earlier, with checking to see whether somebody who's classified as a resident satisfies the definition. We can do automated classification. That is, we can take sensor data and automatically classify it based upon the characteristics of it and whether it satisfies a definition of a class or something like that. And we can perform automated deduction. We can infer new things based upon the data that we have. So one final thing I wanted to say is just give you a quick view of what the semantic web is from an ontology perspective, and then I'm going to give the little example that I promised. The semantic web, simply stated, provides a standard for representing and linking data distributed across the internet. So think about it this way. Think about that knowledge graph, and imagine that knowledge graph that we saw earlier, where the nodes and links are distributed across the world, sitting in servers on the internet. Okay? Imagine that. That's what the semantic web is the distribution of data in a knowledge graph form spread across the world. That raises some issues. So imagine that the University of Toronto and Hong Kong Shuyan University maintain separate databases containing information about their faculty. How could these databases be structured so the information can be easily integrated or related? So if we wish to integrate data from multiple places, we need to agree upon the terms. That is, if we have this knowledge graph that's spread across the world, and we have these knowledge graphs in these two different universities, the very first step that we have to take if we want to be able to link them together, if we want to be able to interpret them consistently, is that we have to agree upon the terminology. Let's take an example of a person, a class or concept called person, and what the properties are, such as what their first name is, what their family name is, what the type is of an individual that is a type person. We need to agree upon this terminology. And if we can agree upon the terminology and we use it consistently, then we have the chance of being able to link this data across the internet. So let's say we have Mark Fox. Mark Fox is a type person. Mark Fox is a given name of Mark. Mark Fox is a family name of Fox, and knows Rita Lee. Okay, well, who's Rita Lee? And that information is contained on a University of Toronto server. Now imagine over at HKSYU, there is a comparable representation of Rita Lee. And it turns out that Mark Fox is known by Rita Lee, and Mark Fox knows Rita Lee. But for all intents and purposes, these are separate. Okay? How do we know that this Mark Fox is the same as this Mark Fox and this Rita Lee is the same as this Rita Lee? I assure you, within the city of Toronto, there's at least 3 Mark Foxes. At least 2 of them I'm aware of, myself and another. Okay? And the fact that I represent my name as a string does not in any way uniquely identify Mark Fox. Okay? Nor does Rita Lee here uniquely identify who Rita Lee is referring to. So we have a very basic problem. To uniquely identify who Mark Fox is, who Rita Lee is, and just as importantly, uniquely identify that this property given name is the same as this property given name here, and this property knows is the same property as knows over here. Just because from an English point of view, that we're English readers, we think that knows is the same knows as here. It may not be. Could be knowing in the biblical sense. Who knows? Or not. I guarantee not. So the point is, in order for us to relate any of this to any of these property names, and even Mark Fox and Rita Lee, we have to have globally adopted vocabulary. So example, there is a vocabulary called FOAF, or friend of a friend, in which they identify classes such as agent, person, and when it begins with a capital, it's a class or a concept. When it begins with a small letter, it's a property or attribute. And so we have an FOAF person has a property given name and property family name. And notice we have a prefix here, FOAF. That is a prefix for the URI, the Universal Resource Identifier, HTTP, XML. I'm not even going to read it all. But the whole point is FOAF person is a short form for this URI that uniquely identifies this concept person. And FOAF, this should be a small letter, not a large. First name is equal to this URI, which uniquely identifies the property first name. So by using that, we can now take our diagram, and rather than it just being person here and just being given name, we now FOAF person, FOAF given name, FOAF family name, FOAF knows. And what this says is that we are using the exact same properties here as being used by HKSYU. So this property is exactly the same as this property. This knows is exactly the same as this knows, because we have a unique identifier based upon URIs, based upon internet standards, World Wide Web standards, that says this property is exactly the same as this property. And we apply that to me and Lee. UT stands for, let's say, this URI with MSF at the end. HKSYU stands for this URI. So now we are uniquely identifying me, and we're uniquely identifying Lee. Now we know everything with the exact same URIs are referring to exactly the same thing. And that then allows us to be able to start linking data across the internet, because we have a global standard for unique identifiers for properties and classes and instances. And all of that can then be stored. We can serialize this graph in the form of a triples in a relational database. So this is referred to as a triple store, where the representation is subject, property, object. So the subject is at the starting point of the arc of the property. The label is the property, and the endpoint is the object. So we can represent this graph structure, or what we refer to as serializing that graph, in this type of triple representation. And then our databases on each of the servers around the world represent their knowledge graphs in this manner, use the URIs to be able to uniquely identify properties and classes and individuals, and we can have applications then send requests to this triple store, or what are called Sparkle endpoints, to be able to query it. And one of the interesting things about this is, normally if you're going to do a query of any database, you have to know what the data model is. You have to know what the structure of the database is. Here, you don't. There's only one structure, triples. That's it. The only thing you have to know are what are the globally used, or the standard set of classes and properties in order to find what you're looking for. So we got rid of totally this whole issue of different data models spread across the world. There is just this triple store that you can query as long as you know what the URIs are. So how does that relate to supply chain traceability? This is work that was done back in the 90s in our group in the Enterprise Integration Laboratory. The scenario is an inspection is being performed on a batch of final product and has been found to be non-conforming. For example, a bad batch of COVID-19 vaccine, or vegetables that have some type of bacteria on it. In order to diagnose a problem, there's need to trace a specific final product batch back to the specific batch of raw materials and start the diagnosis from the first possible point, the batch of raw materials. That is, trace back through each step in the supply chain. And given an entity and a state of the enterprise, can all entities and necessary attributes of these entities that had a bearing on the quality of the given entity be traced and identified? Or how do we trace back when the food or medicine is the endpoint of a complex supply chain? So the types of questions that we want to be able to answer in this scenario are: what are the input resources that can be traced from a given output resource? What activities are part of the path between a given output resource to a given input resource? How much of a resource was used, consumed, produced, released by one or more activities over a period of time of interest? How much time did the activities take that transform the input resource into the output resource? And at what point in the supply chain did activity not conform to requirements? And so this is the issue of traceability, and that I hope is what we're doing is relevant to the whole issue of resilient supply chains. In order to address this problem, we had to develop an ontology of activities, which we did in the 90s in our group, in which we have a representation of activities that are enabled by some state of the world, some description of, in essence, what are the preconditions for this activity to be performed. This precondition could be what resources go into it, what mechanisms are being used, temperature, pressure, etc., can all be defined using this enabling state, and what is the result of that activity, whether it's cooling something down, it's transforming something, it's all caught there. And skip over this. And then as part of the ontology, this is based on Henry Kim's thesis, we introduced this notion of traceable resource unit, where a traceable resource unit is defined to be a homogeneous collection of one resource type that is used, consumed, produced, released by a primitive activity in a finite non-zero quantity of that resource type. And this is critical to the ability to trace back through the supply chain, is understanding what a traceable resource unit, and so we have a set of axioms associated with it. Traceable resource unit is first known to exist at a time that is first used, consumed, produced, or released. The quantity is never incremented after it is recognized to increase. So a traceable resource unit never increases in amount. It only stays the same or decreases in amount. And there's a set of other axioms in here. Individual units of a traceable resource unit are indistinguishable from each other. Hence, traceability within the TRU is not possible. Once TRUs are recognized to exist, aggregating the contents of 2 or more TRUs does not result in the aggregate quantity, maintaining the ID of any TRUs that are aggregated. Once you aggregate things, it's a totally new TRU. It's not the same traceable resource unit. We developed the terminology, the knowledge graph, and the axioms associated with that. I'm not going to go back into that. And what was funny about this is that the motivation here was really coming out of aerospace manufacturing, which I had done some work in the 1980s. And what was interesting about that, after we did that work, we published it, et cetera, we just sort of put it aside and we're moving on to other things. And then we ran across a paper that says, the most advanced theoretical treatment of traceability is that of Kim et al. They described a fundamental necessary core in an ideal traceability system. And this was out of the trends in food science and technology. So we had absolutely no idea that we're having an impact on the whole food industry, the food supply chain, through this use. And subsequent to that, I was involved in some work related to food I won't get into. Anyway, so that's what our example of traceability in the food chain. I just want to put in one other plug. The major focus of my research right now is on city data, on ontologies for city data. And as part of my research in that area, I'm also the editor of what's called the 5087 series of standards for city data in smart cities. This is taking work that I and my group, others in the group, and there's a whole host of people involved over the years in this, have done in the development of ontologies, from TOVE in the 1990s to the Global City Indicator ontology in 2010 and subsequent, and iCity in 2015 and subsequent years. All of that is feeding into this standard that both Megan Katsumi and I are developing. And this is a multi-level standard where the lowest level, part 1 of the standard, is focused on foundation ontologies such as time, location, etc. -2 is looking at citywide ontologies. And the requirement for a citywide ontology or a concept class, etc., is it can be read and updated by multiple services within the city. And the 3rd level, service-specific ontology, which are concepts that can be read by multiple services but updated only by one service. And we're starting off with transportation planning as the -3, part 3 ontology, and we'll move on to other services such as water and sanitation, education, etc. These are the core concepts, ontology patterns that exist within 5087 part 1, as you see here. It's not only ontologies we've developed in our lab, but other ontologies that exist out there, such as time and units of measure, etc. Part 2 deals with indicators, bylaws, contracts, residency, sensors, parking, organization, person, etc. And part 3 deals with the transportation network, transit vehicles, travel costs, trip costs, trips, etc. So in conclusion, I just want to say that when we look back on why ontologies are important for resilient supply chains, the bottom line is the level of intelligence with which we can analyze and manage supply chains depends directly on the fidelity of our models. And so the fidelity of our knowledge representations is a limiting factor in whatever we do in that area. And resilient supply chains is achieved not just through design, but through its dynamic real-time management. So it's often the case when we look at the literature on supply chain management, a lot of the work that goes on within industrial engineering, operations research, et cetera, is more focused on the design phase or the planning phase, and not as much on the real-time management and control side of the supply chain. And that the ability to integrate data from multiple sources with precise semantics, hence high fidelity, is critical to being able to do this type of dynamic management of supply chains. So that's almost the end. I just want to put a plug in that I could talk at a future date about measuring supply chain performance based upon the work that we're doing with city indicators and measurement of city performance and how it relates to supply chain. I could also talk about dynamic and distributed supply chain management, which is based upon work that we did in the Enterprise Integration Laboratory on agent-oriented supply chain management way back in 2001 and earlier. So that is the end of my presentation, and I'm happy to take any questions in the time we have. Chris, are you moderating?
I'm moderating. Thank you, Mark. I think that was a really good introduction to ontologies and to the sort of this invisible thing that's out there that that's underlying an awful lot of the reasoning that happens. We've got time for some questions. So I see Michael has his hand up already. So Michael, why don't you take it away?
Sure. Thanks, Mark. That was really interesting. So you started to touch on this at the very end of your talk. So maybe this is just a conversation for a later date. But what struck me was that these ontologies appear, at least to me, to be somewhat rigid in the sense that if we are conceptualizing them as graphs, that the definitions are sort of set and that the relationships between nodes are also set. But I would imagine, given you all are involved in AI and all that stuff, that there's the ability to sort of have emergent relationships appear within your graphs and things like that. I was wondering if that sort of thing is being done. So for example, since you're dealing a lot with behavior, if a new behavior may arise in a supply chain that isn't already in your graph or your ontology, however it would be said, then would you be able to pick that up automatically, or is that something that needs to be sort of monitored and hard coded in as things move along?
So there's two parts to the answer to the question. The first part is the knowledge graphs are dynamic. New nodes, new links are dynamically added over time. And if you go and you look at what we're doing in the Smart Cities standard, there is a box here called change. And for any particular instance, we can represent how that instance changes over time. So if we're talking about a box of medicine, we can represent what we refer to as manifestations of that box of medicine, and each manifestation represents a changing description of that box. So you have an explicit representation of how that box of medicine has changed over time, what properties are changing, how they change, etc. There's actually, I don't mention this, but in the global city indicator stuff, we also represent the metadata, who created it, when it was created, what the provenance is of it, et cetera, et cetera. So we have a very rich representation and a very dynamic representation of what goes on, let's say, in the supply chain. That's one part of the answer. The second part of the answer is that because the definitions themselves are just part of the knowledge representation, that is, they're represented explicitly within the knowledge graph, then the definitions themselves are subject to change, can be subject to change. That raises a whole nother set of issues in terms of tracking how definitions change and how things are classified, let's say, under older definitions, newer definitions, things of that nature. But we have the ability to represent that. Because we have a general representation of change, we have the ability to represent the fact that something gets reclassified under a new definition, and that the definition itself is subject to change, and hence we can represent the change of those new definitions. So that's the second part. And then the third part is, are definitions manually provided, or are they learned? And that really is an open question, and it depends upon what the domain is that you're working in, and what the nature of the concept is that you want to learn. There are concepts, so view the world at least dividing between concepts that are defined versus concepts that are learned. Okay, a concept that is defined, let's say, is a bylaw, as an example, or the definition of a contract, whereas a concept that is learned may be what a chair is. That is, you look at enough chairs, you may extract from that a general description of that. And so there are a large number of things out of there that you need to define explicitly, and then there are a large number of things that you can learn over time. And determining which is part of what you have to do in order to answer your question properly.
Thank you.
Are there any other questions? Because I'm going to sneak one in if there are none. So I mean, one of the things that I get from this in terms of the effort required to establish an ontology, and I guess one of my questions is about how do you determine if an ontology is fit for purpose? I mean, you started talking about representations that are fit for purpose, and so is there a way to actually, as you're building an ontology, to figure that out or to test if it's fit for purpose?
Yeah. So I didn't go into this part at all, nor explain what competency questions are. But as part of the work that Mike Gruninger and I did back in the early 1990s, is we defined, in essence, I would say, is the first methodology for defining ontologies. And part of that methodology included the creation of what are called competency questions. And a competency questions are derived from a scenario. So you define what the scenario of usage is of the ontology. And then you define a set of questions that the ontology has to be competent to answer. So the representation, the fidelity has to be sufficient to answer the competency questions. And so
I think you want to be on the next slide.
Sorry?
I think you want to be on the next slide.
Thank you. Sorry, I keep looking at the advanced slide on another screen. Thank you. And so the competency questions determine what level of fidelity is necessary in the ontology. So when we start an ontology design, we start with the scenarios, the use cases. We then develop the competency questions. We then go and search for existing ontologies that may address some of these competency questions and reuse portions of those ontologies if we find that they are relevant. And then we extend what we reuse in order to satisfy all the competency questions that we have. And then after that, we validate our ontology by creating an example and testing the competency questions over that application of the ontology. So that's how we do it.
Okay, great. So it's almost like an engineering design process that you've defined for ontologies.
That's right.
Yeah. Okay. Are there any other questions? Tracy, was that a question? Yep.
Yeah, I mean, it's a very naive question, I'm sure, but because a lot of the work that the examples you give are from urban contexts, but I'm often thinking about systems in under-resourced areas, and because you describe this process of making a framework for making meaning within a system of information, and to a large extent, it's a relational framework, right? It's about ascribing value to the processes within that framework and what constitutes a unit of meaning here and there. And it strikes me that that there could very well be indigenous or northern informed ontologies that could help bring some meaning to some of the enormous supply chain challenges. But do you have any thoughts about that?
Well, it's certainly the case that when we look, if we're talking about supply chain specifically for northern communities, there are certainly going to be concepts that exist there that we don't run into in, let's say, southern cities in Canada. And therefore, we have to go through a process of ontology engineering in order to identify what they are. But I don't necessarily see that as a huge hurdle. We have to start with that scenario. We have to identify the competency questions, and then we see it as an extension of what we're currently doing. So, would we be starting from scratch and dealing with northern communities? No, it's probably 95% of what we've done applies, and then we're looking for the other 5%, 10% extension to adapt to any unique characteristics of that we haven't captured yet in our ontologies with respect to indigenous communities. Now, you have to keep in mind that that just because they're indigenous communities doesn't mean that they don't have concepts such as vehicles. They don't have concepts such as food and supply chains and things of that nature. I mean, all those concepts apply. There are just some other concepts that we may not be aware of that may be more culturally sourced, if you will, that we don't represent at this particular time, and we'd have to do that. The big challenge that I have, I started looking, I'm involved in another project which is called the Urban Genome Project, which is looking at evolutionary theories of cities and communities, et cetera, including northern communities. The biggest challenge that we have is not the desire to address the northern communities. It's the hurdle in getting access to indigenous communities, given their experience in dealing with researchers who come in and do things without their permission or say things that shed a negative light. And so so that for me is a bit of a hurdle. And I've even gone through, what is it, OPAC certification? Which OCAP, yeah, OCAP certification in order to be aware of a number of the issues that exist in dealing with northern communities with respect to data.
Yeah, sorry, Michael.
I was just going to I put in a link in the chat, Tracy, that you may be interested. There's a professor that was at my grad program who did applied spatial ontologies with indigenous Australian communities. So there is a body of work around this. This was more in this world of geographic information science. So how do we conceptualize? How do we put things in computers to represent space? But like they struggled with a lot of things, like there was no word for river. So like, yes, there is a thing that is a river, but it comes and goes. And so some of the points that Mark made, like the thing may exist, but how we know it may differ. And then how it's coded in a computer could be a little more tricky. I don't know if that's I don't mean to overstep, Mark. Is that sort of in line with what you were saying?
It's certainly the case that there are concepts that we don't have in southern communities, and there are ways of viewing the world that are different. And I think this issue of an Australian community where there isn't a concept of river, but I don't know what the concept is of things that flow and change over time. They're not the same. Would be very different than what we think about. But that doesn't mean that you don't represent a river. It means that there's alternative ways in which you're viewing a river.
I guess that leads me to ask, though, how do we make meaning of varying determinations of value or success or challenge in these models, right? Like, how do we define what is working and what isn't? Because that is so contingent on, your language and your worldview and the space in which you live. So is this, because it's been developed in urban spaces, is this very urban-centric Western, work, or does it have that kind of dynamism? Could it be applied across a wider range?
I don't see any reason why it can't be applied, but it gets back to the issue of scenario and COMPSI questions. Well, I understand that whatever you do in northern communities is done within a cultural context that is different. We have to get back to the COMPSI questions, which may have to capture that or may not have to capture that. Okay, but I'm not the one who defines the COMPSI questions. It really comes from the community itself. So if we're talking about resilience in supply chains, whether it be food or medical, that community first has to define what their scenarios are, and what the competency questions are that they want to have answered that address their needs. So our intent when we go through this ontology engineering process is not to impose a particular perspective, but to understand what the perspective is to have that perspective imposed upon us.
All right, I think that was a very interesting discussion that came out of that, and I think we're well over time. So I think I'm going to ask all of you to thank Mark, and I'll thank him as well for a very interesting discussion. And as Mark pointed out, next week we have Dr. Megan Katsumi, who's also going to be talking about ontologies in the context of understanding transportation data. And so please all come back next week. Thanks, Mark.
Great. Thank you. Good seeing everybody.
Thank you. Goodbye.